It's a pleasure to be here. What I'm going to talk about is sort of a two-part talk in a way. First half is sort of relatively general motivation and generally some little bit of state of the art, and the second is a couple of research ideas that come out of the sort of the more pragmatic considerations that I'll discuss in the first part. So this is work of many people. We have a fairly large group of people working on natural language parsing and semantic interpretation at Google, and they also have a number of academic collaborators that mentioned there at the University of Massachusetts, at the CMU, and that we work with to try to push forward the boundaries of what you can do with semantics in a large-scale text analysis and understanding. So I have to get slightly organized here. Technology sometimes has its problems. So it's a very nice place. If you like mountaineering, this is one of the most beautiful mountains in the United States, called Mount Shasta in Northern California. I like to go there every the spring to go ski pretty high up. So you don't live there, unlike me, so you might want to know something about Mount Shasta and how to climb it and so on. So there are good news and bad news about that. Let's go first to good news, which is, I'm sorry that I'm having some technical challenge here. So these are the search results that Google presented a few days ago for Mount Shasta. So on the left-hand side, you have standard search results. You have an ad at the top. And then you have the Mount Shasta Wikipedia entry and some images and so on and so forth. And there's a town called Mount Shasta that's mentioned later, below Mount Shasta Chamber of Commerce. The mountain doesn't have a Chamber of Commerce, it's a town nearby. And so on. And then this sort of lower down you have search results about climbing and mountaineering on Mount Shasta. That might be something you're interested in if you want to go there. Then there's other stuff that is on your right side, right? Which is new. It's what we call a knowledge panel. Is something was launched a few months ago. I don't know. Actually, it's sort of been launched for the whole world. It's certainly available in the United States and other countries. And what's kind of interesting there is behind that there's this data structure, very large data structure that has been being built at Google called the Knowledge Graph. It's essentially a linked data system, and that links different knowledge resources, including maps. You see that map there that has an annotation for the action for that particular entity. Pictures of the images associated with the entity, and a lot of linked data, things like the elevation and other attributes that are stored in Knowledge Graph, which is essentially it's a simple but fairly powerful knowledge representation system. And if any of you has played with Freebase or used Freebase, so the company that developed Freebase with MetaWeb was acquired by Google a couple of years ago, and they came into the company they've been developing this technology further for use within Google. And a lot of the work I do these days in close collaboration with them. So this is nice, gives you some basic information about the mountain, and now you can see the potential that we have all this structured information about entities and concepts in the world, and which might allow us to do more richer inferences in doing information retrieval and any other tasks that we might be interested in. Now, let's say, so I want to climb. What should I do? So one thing I might want to know is where to start, trailheads. So if I do that search, I don't have the nice set of results there on the right anymore. I have just the usual kind of search results. And it turns out that they are not as useful as I would like. For instance, this one actually doesn't have anything about it. Only talks about one Trailhead, so which is the most popular one. It's probably the one I don't want to go to because it's too crowded. And so on. If I do a bit of click links, eventually I find this guy. So for instance, the second one. It's actually not a bad search result. I can look at it. And I see this. Now, nothing about Trailheads. Some quote from some book, some ads, some statistics which I had already gotten before, and some additional ones. But I'm kind of lost. Why am I looking at this? Now it turns out that I'm looking at this because lower down, way down, you have this stuff. Oh, that's what I was looking for. But the search engine found that the term Trailhead existed in this page in a prominent in many times. So this is a good result. It turns out this page is pretty good. But the information I wanted is further down. The search engine doesn't realize that if I'm looking for Mount Shasta Trailheads, I really want is this thing. Because it doesn't know the concept or what it counts as a relationship between a mountain and something called a trailhead in that mountain that has some name. Let alone know, for instance, that I might want to know more things about those trailheads, like for instance their elevation. And some of them have the information here, others don't. Now if I go on the map, I can find the elevation of all those trailheads. But of course it's not here. And I don't have a way of joining that information. So actually what I really like to do is to ski down. And I don't like the climbing so much, but skiing is pretty cool. So I might ask that. Well, so this is conceptually is fairly simple, right? Mount Shasta ski routes, But the problem is most of the results there is about this thing called Mount Shasta Ski Park. Mount Shasta Ski Park is a small ski area at the bottom of the mountain, which I don't have any interest in. So these three results are wasted for me. They don't not what I want. So the top one actually is the right one, but okay, a lot of statistics again. Still nothing about the routes. Actually, so I can. By the way, notice that elevation is different from the elevation that the knowledge panel said. Only by 8 feet, but still. Why don't we kind of agree about these things? Or at least say, well, maybe it's in the range, right? Actually, there is this thing lower down. That's pretty good. It's a table with everything, right? The routes, and then there's a lot more information that are truncated, where you start, etc., ratings. This is beautiful structured data. But I don't see the structured data. It's all kind of there in a big blob. So these are the challenge that we have, right? We have the glimmers of the ability to look at these things not as pages, not as strings, but as concepts with interesting, meaningful relationships between them. But we are very far from being there. That's a challenge for our entire community. So some lessons so far. So there's this slogan that my colleague and the senior VP of search, Amit Singhal, uses, things not strings, and when he talks about knowledge graph, which I really like. It's short and sweet. It's good. Provides join keys that allow you to join different types of information. It's very important. And you can think of it as providing a semantic index. Now, the index is no longer just keywords, it's actually concepts that you can, hang information from. And so that's great. But most information is still in text, and tables, and. So what we really need is to link those things, or representations of those things, and the text we have. That's the natural language processing challenge that faces us. So I want to make a detour here because it really explains the tack we're taking in this work. And I like to call it no tech transfer. I think the concept of tech transfer is deadly for our field, for all of our activities, whether we are in industry or in academia. First of all, we came to this work not because we had something we wanted to sell, but because, in terms of technology, oh, I have a technology, what can you use it? But rather because we were spending a lot of time looking at problems and opportunities in search. What search users struggle with, what they cannot do, what frustrates them. And we got involved in building this work by building simpler things, doing simpler tasks, where our skills complemented other people's skills within Google, so that we could build trust and they, get the other teams to say, oh, these guys know something. They are helpful. And at some point, then we say, well, we are ready to start betting on something bigger. We know what we need now at some level, but it's a risk. It's always, you have to take risks. You have to make bets on these things. Another point I want to make is we measure. Not just internal quality metrics, but also ones that are directly relevant to the output that we provide to our collaborators within the company, with whom we work to develop products. And in many cases, although that hurts me as liking, fancy technology and fancy algorithms, effectiveness trumps novelty in many cases. Make it work before you make it fancy. But continue to do research. That is, what is really interesting is how you manage to be both engaged in things that are very product oriented and things which are really cutting edge, by maintaining a healthy and connected research program that essentially broadens your opportunity. It's like your investment for the future. So with that, it gives a setting for the sort of spectrum of things I'm going to talk about for the rest of the talk. So what we know to do is to think about the task of connecting text to the knowledge graph, to knowledge resources, knowledge bases, as sort of a translation and linkage task. Those of you who work on statistical machine translation can think of the alignments. We just trying to essentially do a certain kind of alignment between resources, between text resources and knowledge-based resources. And so natural language text, knowledge bases, which are fundamentally key spaces for joins. This is really where the big value of knowledge base is. Not the ontologies and all this other stuff. It's basically, I have unique keys for things. So when I'm talking about Mount Shasta, the mountain, I can distinguish that from Mount Shasta, the town, and be consistent about it in all the things I do for my users. Semi-structured data. There's a very nice program in research in semi-structured data at Google that led by Alon Halavi, with whom we collaborate a lot. And the crucial thing here, and that's why I call this low-pass semantics, is that accept lack of detail. We are not doing semantics like the kind of logical natural language semantics that I was involved in doing in the 90s. Not because I don't think that's good work, or that should be, but because we can't get there yet. But we still can do something. So let's do that something and see what much further we can go. So the way I like to think about it is, once I do these linkages, I can do certain inferences. They help me do certain inferences. If I do those inferences, I can get some glimmers of meaning. I can get, if the right inferences are made, then I can start saying, oh, this machine understands me. So that's the sort of the model in which providing even this very weak notion of semantic for text can help us really get towards understanding machines. So now I'm going to talk. So basically, the kind of systems that we're building are not very different from what you might think, and they are fairly traditional in many ways. So we parse, and I put this in gray because I'm not going to talk about that. look at referring expressions, classify them, do within document co-reference, and all these things we try to do well, but we put up with their imperfections. And then I'm going to talk a little bit about entity resolution, deciding when multiple mentions, even across documents, mention the same thing, and how from seeing certain co-occurrences of entities you can infer certain relations. These are the two researchy things I'm going to talk about. We have existing solutions for these, but we are building on them, doing further research. So I'll show you sort of a simple example of putting all this stuff together. So I don't know whether you can read that. There's a little paragraph of real text from somewhere on the web. It's about some guy, I don't know, called Eric Wesner. And there's some voice coming from somewhere that I don't know what's in. We can we do dependency. You apply dependency parsing. I don't know. It's a sort of a strange. It's like a Greek chorus somewhere. But it's of one though.
It's just someone phoning and don't care. Yeah. Okay, just go on.
Okay. So we do standard dependency parsing, which again we try to do really well, but it fails sometimes. And then we identify potential referring expressions like proper names and pronouns and common nouns. And try to classify them. In this case, red is person, yellow is location. There would be also other classifications if we had them. And then we categorize, try to group them further. For instance, we know that Eric, we believe that his refers to Wesner, and his refers to Wesner, and the Wesner refers to Eric Wesner as well. So all of those in our single co-reference cluster. We got this one right. We often get them wrong. And we also guessed it's masculine because it's referred to by his, and has Eric as a first name, which is kind of male named. And then we also noticed that there are these places, Poland and Raleigh, North Carolina. We actually can figure out what they refer to in the knowledge graph. These are easy. And that's where that says profile is points to the knowledge graph entry. But the other things we can do is we can look at certain relations. We have these patterns that we have induced by certain algorithms. There's one algorithm I'm going to talk about here, but there's others that we've also been exploring. That says for place of birth, born and raised in is a good pattern. And so basically, I did something. I'm sorry. I was doing, but I wanted to go back one, but somehow this doesn't allow to do that. And so that allows me to find this relation of being born and raised, and we find that this guy was born rather than. So let me mention something which is important here at the end of this part of the talk, which is that natural language processing really matters. So people often say, we can do this kind of entity tagging, you can do name entity recognition and relation extraction just from shallow pattern matching, no parsing. Who needs that? Well, I'll give you some numbers. So this is an example. I won't go into details of the example. We are doing some relation extraction and say we use just text patterns, no parsing, no correct, anything. And you see the numbers there, known triples. These are the ones we actually know are have in our knowledge base. and then the unlikely correct ones are, by certain criteria, we estimate that those additional ones are also potential likely to be correct. So if I instead use not just the text, but parsing with a very slow and very accurate parsing, or more accurate parsing, it's not really very accurate, I get way more of triples extracted. Triples are entity relation entity, right? And a lot more correct ones. Now, if I throw in coreference, within document coreference, look at that number, those numbers compared with the previous numbers. So if anybody tells you, oh, we are doing all this linguistics, you can say, well, there are reasons, and practical reasons for that. By the way, if I use a less accurate, much faster parser, I lose a little bit. Not a lot, but a little bit. I just kind of wanted to give this to say, there's hope. It is. The things we're doing actually have value. We have to just figure out ways of getting that value out and putting it in practice. So I'm going to talk about inference and learning in the rest of the talk, and there's just 2 examples of the research we're doing. And this is not, take your machine learning package out of the box and lots of machines and do something. This requires really designing things for these particular problems. So we have, of course, fairly efficient computational infrastructure, and I cannot emphasize that too much. A lot of the things we're doing, at the scale we're doing, depend on having the most efficient data centers there are. Not by any fancy algorithms, but really being able to use lots of computers efficiently. We also have built a text analysis pipeline that's scalable, that's always improving. And I cannot actually tell publicly the scale at which we run this stuff, but I can say that we are very happy on the progress we're making. And problem-driven, let's go back to my point, methods and evaluations. Think about what it is that you're trying to do. So I'm going to give 2 examples. One is this distributed large-scale inference project, which is just an exploratory project that was done by Samir Singh, who was a graduate student at UMass who spent the summer with us a couple of years ago, and we continue to work with that team. We actually fund UMass significantly to work with us on this problem. And it's a problem of cross-document correctness. You have many mentions of Kevin Smith, and it's also this guy, this nickname, Lovebug Starsky. Actually, this turns out the true name of that guy is Kevin Smith, but not the same Kevin Smith as the other Kevin Smiths. There's an author, a rapper, filmmaker, firefighter, a running back in American football, and a cornerback in American football. So there's lots of different people with that name. So we'd like to figure out which is which. And by the way, do this for Kevin Smiths that don't exist in the knowledge graph, because knowledge graph is always incomplete. So we're going to look at this as a sort of a graphical inference problem of a particular kind. I'm going to sketch it very quickly because I don't want to have any equations here. So we think about mentions of Kevin Smith, say, and you try to cluster them and essentially draw a graph where pairwise we look at 2 mentions, say, do they look compatible? Do the contexts in which these 2 mentions occur look plausibly similar contexts? And and the others that say, do these look really incompatible and distinct? So we have 2 types of edges in this graph, the ones that vote for I'm in the same entity and ones that vote for different entities. And then what we have to do is come up with an initial hypothesis for our entire graph, which is all the mentions that we have in very large collection documents, and then try to iteratively improve it. And when we do this, is to take an existing configuration and then try to change it to a new configuration that with high probability is more likely configuration because puts like things together more and puts unlike things apart more. And we do that essentially with a randomized search algorithm. It's also a particular version of Markov chain. I don't won't go into that. And one of the kind of cool things about doing it this way is because we have this huge graph, there are many people that we're talking about. Some I call Kevin Smith and the others call Mary Smith. We can deal with them in different parts of the graph. And if we organize our graph properly across multiple machines, we can do these things independently and do the exploration in parallel. So, you start with a set of candidates and inserted clusters. We distribute them to a bunch of inference components. Each of them comes up with a new shuffling of things, and we keep moving these around. And this approach allows us, and these are curves, don't worry too much about what they really mean. I mean, actually, this is not the best curves we can get for this problem. These are just some early experiments, but are informative. Wall plot, that's running time horizontally, and vertically is accuracy you achieve. With one machine, it's going very slow, and the accuracy is fairly low, but it's on a very hard task because on a very large number of entities. If you throw two machines, you can do a lot better. 3 more, and you keep going, you can get a lot better. And in fact, with some additional techniques that I won't go into here, you can really get very good results on this task. This is work that Samir Singh's thesis would be about. So we did some large-scale experiments where we extract and filter all web links that point to Wikipedia. So we know those links refer to Wikipedia pages. There's some filtering needed. It's around 1.5 million mentions. Actually, there's a much larger data set that we are about to release to the public of this, so that people can work on this problem, which I can't remember now the size, but it's like, I think, 20 times bigger. To give you a sense of how well this does, with the approach that I described, and again, the numbers are just for relative magnitude, I won't go into the details of them, is that basically we start with some baseline, which is sort of a link to some most likely clusters, something else which uses a spectral clustering algorithm, another method which really works significantly better. And in fact, Samir since this has done a lot more to make it even better. The point about this work is simply to say that you can actually do very large scale inference of interest for a problem like this, which is identify mentions of entities in documents to figure out, are these entities the same or not? In a fairly effective way, with fairly simple algorithms, provided that you know how to do the parallelism reasonably well. So the other example that I would give, it's a different one, is about relations. So this is very recent work. It was started by Mi Lau, who was an intern in our group last year. Mi is a student at CMU or is about to graduate and is coming to join my group. And then with Amar is a colleague of mine, and William Cohen is a faculty at CMU. And so this paper is going to be given at the MLP soon. What we looked at is the following question. We have these freebase, these knowledge graphs, I say freebase, and we have text that has been analyzed. Can we jointly connect the two to get better results at finding relationships between entities that have not been expressed in the knowledge graph than just working with either alone? So what we're going to do is think about paths in this graph. The graph has several types of edges. It has edges that correspond to edges in the graph, like has, let's say, profession or has father. It has edges that correspond to structures in the text, such as coreference edges and the dependency edges. And then we have these entity resolution edges, which are edges where we decided that person that mentioned Charlotte refers to that particular entity, that particular entity in the graph. And I won't go into the specific method of resolution we use for this work, although it's very simple and it's not the best we could do. It's just one that we use for purposes of publication. So we're going to take paths and path types. A path type is basically a sequence of path labels, so of edge labels. So for instance, it might be something that says profession or profession, and then go backwards to an edge that says has father. And we're going to consider random walks in this graph up to a certain length. We're going to learn weights on these path types, which are just strings of path edges, edge labels, to favor desired walks that lead from an entity to another entity we know it's related in the desired way to this one. And I will see an example in a minute. So, and we're going to do is going to try to extend freebase. So freebase, the version of freebase we worked with, it has 21 million concepts, 70 million edges. And we found 60 million web pages that mention freebase concepts relevant to this particular experiment. And we got to three relations: profession, nationality, and parent. So we're going to use very simplified entity resolution. We just, for each mention in a correct cluster of correct within document coreference, we're going to just choose the most likely concept. So all Clintons are going to be Bill Clintons. Now, this is a simplification. We could do much better than that, but we didn't want to clutter this particular experiment. So here's an example for profession. There are around 2 million people in Freebase, and only 300,000 have a recorded profession. So we could hopefully find some professions that are not there. Furthermore, it's a very biased sample. Up to almost 250,000 of those are politicians and actors. Guess what? Right? So, poor computer scientists and linguists are not very highly featured here. So what we're going to do is to take, we're only going to consider path lengths of up to 4. So fairly short paths. And we're going to say, does this path suggest profession? That this person has this profession? So positive examples, we're going to use machine learning. Positive examples are pairs that are in Freebase in the profession relation. So for instance, Michael Jordan, basketball player, as opposed to the other Michael Jordan. And negative examples are it's actually tricky. There's some subtle sampling mechanism we use that's discussed in our paper. I won't go into that because we don't have explicit negative examples, but we can look at things that are not in Freebase and do some appropriate sampling and get a relatively good negative set. Doing some cleaning of data and just sampling, we get this training and test sets to do this evaluation for profession, nationality, and parents. So here's an example of a learned path for a path type, actually, for profession. It's not a very good one. I'll see, but it doesn't matter because we are going to put weights on them. So let's suppose I know that John Coltrane is a musician, and I see that there's a mention of Miles Davis and John Coltrane. This is the actual piece of text. So there's a mention add from the D Miles Davis to the mention of Miles Davis, and the mention -1 inverse from the mention that John Coltrane's phrase to D John Coltrane. And we're going to just say that if two people are mentioned, if there are two entities that are mentioned in the coordination quite a bit, and furthermore, one of them has a profession, the other one might have the same profession. Might. It's not guaranteed. We have many rules like this. But here's some interesting results. So if so this is, again, I won't go into the details of the numbers. The point I want to make on this one is say, let's see profession. If I use the knowledge base and the text, I do better than using just the knowledge base to do inferences of professions to fill in gaps. Because you can do it just from the knowledge base. Because if you say, for instance, someone is a basketball player and someone else and he's a member of the LA Lakers, and someone else is a member of the LA Lakers, he should be a basketball player too. Well, of course, he could be a coach, but That's why this rule is feasible. So if you look at actually human evals on the data that at precision 100 for the top ranked 100 professions we get a fairly high precision, and even at the 10,084% is actually better than anything we've seen before. And in coverage we get also very good results. So for instance, if you're looking at professions that we extract, for 100,000 profession triples extracted by this method, they cover 79,000, over 79,000 people. So this is not just the same person again and again, or things like that. There's a lot of variety here, and as we see, this is actually doing reasonably well. It's probably not good enough, certainly, to show it in the knowledge panel, but it's good enough as material to combine with the information to help us fill in missing information in the knowledge graph. It can be scaled up, because it's based on random walks. You can start many random walks in parallel, and by indexing the text by them mentioned in terms of the entities they mention, you can do this really, really efficiently. This learning and application. So, kind of final thing is we have no excuses. Basically, we have good language analysis components, not as good as we'd like, but good enough for starting to think about the web, not as like blob of text, but actually a huge knowledge base, which is just noisy and kind of diverse. In combining all these weak sources of evidence into sort of in text and structured data, and to support really interesting inferences. So when I start drawing these relations like profession, I can start help ask queries much better, because I now have evidence about a particular way in which entities are separated, say by profession, that people, in this case people, that can help me answer the queries and present the related information. So my point, kind of final point of this talk is we can do really, the language technology is at the state that we have real practical opportunities if we really invest in solving actual problems. And all of this technology that we're developing here is on the service of trying to enhance how I can use, structured knowledge resources to help interpret queries and help interpret documents and connect them more effectively. Thanks.
So even though it's late in the afternoon, we have time for questions. Are there any questions? Yes, please.
What do you mean by the low-pass semantics? What's the substance and the difference between the semantics?
Well, so it's low pass because there are many things we're not looking at here. We're not looking at, semantics, negation. We're not looking at modality. We're not looking at, deeper, sort of propositional aptitudes. That is just about anything you can think of that would lead to a published paper in semantics is not here. What is here is simply figuring out what entities and concepts are being talked about, mainly entities with some concepts as well, like professions, for example. Figuring out some subset of the relations between them, but not necessarily whether we don't have ways of deciding well on their truth values, for example. If someone says, I do not believe that Michael Jordan was always will always be a basketball player. What can I say about that? I just say Michael Jordan, basketball player. That's all I can pick out of this. And I might say, oh, he is a basketball player. I don't have any way of saying that dealing with the tense or aspect in something like this. So that's why it's low pass. You see, like this low pass filter, you only get the low frequencies. Here I only get the low semantic frequencies. The high pitches I cannot hear. I'm kind of deaf to. But I still can do something in the same way as, think about the old style of telephones that had only up to 4 kilohertz. You could still talk to people. You know, you do, and now, you know, if you have higher quality, higher fidelity semantic analysis, you'll be able to do more. But let's do what we can do already, or try, or at least explore what we can do it for real, for practical purposes.
Are there any? Yeah. Okay.
Very interesting work. We are working also with the freebase and the large-scale relation extraction. I have one question. For the large-scale information extraction, we are always facing with the evaluation challenge. I see the coverage you use the existing freebase and see very good. How did you have solutions for new discover? Because information extraction relationship, you want to discover new information. Did you conduct any actually large-scale evaluation for new extracted data?
This is a very controversial issue within at Google, because we try to decide how much we can rely on automatically extracting information, and this is not my decision. It's a more complex decision. We've done some experiments where we had, fairly extensive human curation of extracted profession data, and we got some fairly nice results. These results are different. These are much more superficial evaluations, but still they are more than typical. What's typical in papers that people have published so far, at least the ones I've seen. But you're right. I think ultimately where we're going to get some evaluation is in some of the things we're doing at using relational information in other parts in other products, and seeing how changes in intrinsic metrics correlate or not with this application metrics. That's underway now, but we haven't. I don't have anything to report yet.
Joseph?
Hi, thank you for the talk. I'm thinking about alternative baselines for what you've done. There are relatively simple and straightforward ways to learn profession labels from data. Professions such as X, in terms of patterns, similar to what you've done. So and for professions, you can do that with quite some reasonable accuracy. If you had done that and then used some distributional idea, kind of like just mention of profession and the entity that you're interested in, like Miles Davis, in a particular sentence where sentence boundary detection is also reasonably okay, would you have gotten something that's actually much better than what you ended up getting?
Well, I think the answer is sort of in the talk, is that if we just use patterns on the text, we have worse results. If we do, I mean, we've done the experiments.
No, but it's a different way of doing it. So you learn.
No, it's not. Trust me. I've done this. We've done the experiments. I don't have the time. This is not the technical talk, so I don't have the time to go into all the experiments we've done. We've done many experiments on this profession extraction problem. These and a bunch of others that are not yet published, but will be. And the point is, when you combine syntactic. So if you combine deeper syntactic analysis of the text, and also including coreference, and if you also complement relations that you have in the text with relations externally knowledge base, you can get better yield at a given level of correctness than by using the text. That's, I have plenty of evidence for this, not just from this paper that's going to be in the MLP, but a couple of, other work we've done. And the other thing is, I don't need to restrict myself to text patterns. Why should I? I could do the richer things and get better results. Why should I be restricting myself artificially?
That was Khalil?
Yeah, so I'm happy to see that parsing finally pays off somehow. Parsing in general was intended to give you a predicate argument structure, which links with what we know from the past, logical semantics, which in itself somehow missed lexical semantics, you know, the actual representations of what the entities are. How do you characterize this low-pass semantics in this picture? Does it relate in any way, or is it just something completely on its own? Does it connect with lexical semantics? Would you imagine the, you know, I don't want to call it old-fashioned logical semantics on top, but can you imagine that something like that, we talked about it a little bit, but I mean, I'm curious to how you see the connection between these different...
I mean, this is I had to have a title for the talk, so I chose this one because it's kind of a bit of a pun, and also because it characterizes the way I see it, which is there are many different ways of thinking about, many semantic theories and many interconnected but somewhat different notions of semantics. And I'm not making sort of any kind of hard theoretical commitments to any particular method. I'm kind of very eclectic in what I use. It's low pass because, as I said, there are many things it doesn't see. And what the things we're trying to see are entity reference, basic sort of relational structures, and rely a little bit on lexical semantics in the sense that the nodes in the knowledge graph carry with them not just the identity of something, but also some attributes and relationships for that, which can be used in helping us disambiguate. So in that sense, we looking at lexics, and so knowing that, for instance, people do have professions, but cities don't have professions. So that's a very simple form of sort of selection restriction based on lexical semantics that's useful for some of the things we do. So we draw from, we have no pride here. We'll draw from anywhere that works. And because our goal is not to be necessary to be new. Our goal is to be useful.
Thank you so much for your talk. I think I have to close at this point now. Thank you very much again to the speaker.